Hi, everyone, and welcome to the third episode of the Coding Challenge. I'm your host, Kabul, and today we have a very special guest with us in the form of Petru. Hey, Petru.
Hi, Kabul. I'm a process development engineer working at Renishaw. By training, I studied electronics engineering at the University of Sheffield, but I did a 1-year industrial placement with National Instruments, where I got introduced to LabVIEW, and since then I seem to have done more LabVIEW and software engineering than electronics. So that's what I'm mostly doing in my current role as well.
Oh, cool. So I'm hoping that most of our viewers would know what LabVIEW already is. So what part of LabVIEW do you enjoy, and what do you do with LabVIEW?
In my role, we use LabVIEW to create mostly test and assembly systems that help my company Renishaw to build the products it's trying to build. Obviously, the more automated you can make your production line, the more efficient you can be. And so myself and my colleagues, we are always trying to improve our assembly processes to reduce the time it takes to build our products, and to obviously ensure very high quality in assembling those products. To do so, we use LabVIEW mostly to build Windows applications that run on normal Windows computers. Obviously, we have graphical user interfaces for the operators and technicians and engineers that interact with these apps. But also sometimes we use real-time targets, such as compact RIOs or a real-time PXI controller. And obviously, we use LabVIEW on those targets as well, sometimes on FPGA targets as well. But more often than not, those targets ultimately report to a Windows GUI.
So from your university days, you obviously didn't start off with LabVIEW with programming. Did you? What was your background back then?
In university, when I joined, I didn't know that much about software. I only did a bit of C++, C programming in high school. And in university, in the first 2 years, I think we had a module or two on C programming. It was a very good introduction, but obviously it was just that. When I went to National Instruments for the industrial placement, I hadn't opened LabVIEW at all prior to joining NI, but obviously when you're there, you learn a lot from the people there who are kind of the best teachers. So yeah, I feel like it was a great opportunity, and learned a lot about LabVIEW since then.
Oh, awesome. So what about your challenge today? So you've obviously seen a couple of the older challenges that we've done. Well, older, the 2 that we've done so far. Do you want to tell us a little bit about your application? Feel free to share your screen and try it.
Absolutely. Then I guess I'll go ahead and share my screen. Okay, so I think I'm sharing my screen now, hopefully.
Yeah.
And one application I built a few months ago, I think we finished working on it at the end of March, is this project here called the Night Tour. So I'll go ahead and open the code. And possibly even better than showing the source code, maybe I can show what the app does first. And I've got an executable of it here. So I'll launch the executable.
I see you're using the Community Edition. Have you found anything exciting about Community Edition as pretty much 2020?
I haven't explored all the new things that are new in 2020, but I think the fact that there is a Community Edition for the first time is hugely important.
Awesome.
This is the app. there is an about page here, which hopefully, well, I try to give an introduction to what the app is trying to do. And possibly the quickest way to understand what it's doing is to look at the picture here in the top right corner, where you can see a knight that jumps around on a chessboard-like pattern. And it jumps around, covering each square only once. So the goal is to cover each square on the chessboard, but without revisiting any square more than once. As you can probably tell, this is the type of problem that computers excel at. But it turns out that even though a computer can kind of rattle through these possibilities and do so much more quickly than a human can, when you're trying to find all possible trajectories on an 8x8 standard size chessboard, it turns out that to find all those trajectories is quite a challenge even for modern computers. It's one of those problems that kind of seems simple, but the sheer number of possibilities is tremendous.
So I suppose with the GIF you've got going on there, or the animation you've got going on there, I love the pattern, by the way, that the lower animation generates. Is that how many different combinations of routes are there for it to occupy each of the space only once?
I can't remember the exact number, but if memory serves,
more than one?
Oh, it's something like 18 million billion or something like that. It's a huge number. Yes. And it's all very well documented on this first resource link, which is the Wikipedia page dedicated to this problem. I should also mention that this problem has been known and has been a favorite problem for computer scientists and kind of just getting started software engineers for many years. I think I first heard of this problem when my programming teacher in high school mentioned it to us, and I think she gave us a solution back then in C++, if I remember correctly. But obviously, I didn't write the solution myself back then. I just saw it running, and I was quite impressed.
Cool. So here's your big question of the day so far, Petru. Did you cheat and copy the C code and convert it to LabVIEW for this?
No, I didn't.
Okay. Okay then.
Should I go ahead and run the app?
Yeah, that sounds awesome. So what we'll do is we'll put all the links that you've got on there on the description of the video later on. So yeah, that's perfect.
Absolutely. Yep. So I try to make the GUI very simple and intuitive. And the one thing we need to do to start the app is just to press the start button. So by doing that, you can see it started rattling through the tours. And you can see here the number of tours it's finding. And so each tour is a complete sequence of 64 squares on an 8x8 chessboard. This is the number that I mentioned earlier, that the total number of tours is something like 18 million billion. So as you can see, even though it's finding the tours very quickly, which I guess you can expect from a modern computer, it's going to take ages to find all of them.
Yeah. So I'm assuming that you're, while you're going ahead and finding each one of the tours, I'm assuming that you're you've got a log of all of those so you don't repeat them again.
Absolutely. It's keeping track, so it's never repeating them, and it's also logging them to a certain text file, which is we have the file path here, and we can log two different types of messages. This type is the minimal type. It's kind of like the minimum amount of data you can write to a file for a human to easily understand what the tour is about. You could make this string even shorter by writing in binary or something like that, but that would be harder for a human to understand. And I also made a more detailed version where it gives you more information. It contains the minimal format that we saw before, this part, but also gives some more information like the total number of seconds taken to find that tour, which is here, and other useful information to kind of troubleshoot and find out what's going on. One particularly interesting aspect is, by the way, I paused the app just for a second so that it doesn't keep updating this page. But one interesting display is this, what I call the chessboard format display, where you can see the order of the squares the knight stepped on. So you can kind of follow the path of the knight. So it starts here at square 01, which is the bottom left corner, which in chessboard terminology is the square A1. And then it goes to here to 02, then goes to 03, 04, 05, 06, and so on. And you can follow visually and verify visually that it's actually covering all the squares and is doing so without repeating them. And if we open the file in a text editor, for example, in Sublime, we can see here all of those tours being logged. So obviously you can go later and verify that indeed it didn't make any mistakes and it did cover each square only once. And I did do that as part of the testing. So I'm quite confident it doesn't make mistakes. And you can see when we changed from logging the minimal to the detailed version, it makes that change in the log as well. So essentially what you see on the GUI is exactly what is logged on into the file. So I wanted to have that. Yeah.
Cool. So in my previous video, when I did with Jonah, where we were trying to explain what iterative brute force algorithms are, where you do a certain thing and you go through all of the possibilities. So for one of these tours that you're calculating, so I'm really intrigued to see what the code and your explanation about how you go ahead and build up a big log, because I can see that getting slower over time. Is that fair or?
Yes, so it does get slower over time, but I think in this case it's not due to LabVIEW keeping more and more data in its memory, although my first implementation did that. I think the reason why it's getting slower is simply due to the nature of the algorithm that we're doing. And as you very well said, it is a brute force algorithm. There are other algorithms out there, but I just wanted to start off with the kind of most natural, most easy to understand algorithm, which is the brute force one. In here in the About page, I actually mention a little bit about something called the Warndorf's rule, which is something I learned from the Wikipedia page. And without going into too much detail, I believe that by applying Warndorf's rule, a consequence of that is the fact that the app finds easy to find tours first. And then as it keeps finding more and more tours, it exhausts the easy to find tours and starts getting into the more difficult to find tours. And that's why it's taking longer and longer. So that's at least my perception. I haven't fully tested this, but I think it's more likely that it's slowing down because of this rather than because it's storing more and more elements in memory.
Awesome. I'm really looking forward to looking at some code and trying to go do a bit of a deep dive into that. Is there anything else you want to talk to us about here on the screen?
I think we pretty much looked at most of it. Obviously, there are some metrics here. And you can kind of navigate through these pages, through these reports by going previous and next. One thing that might be useful would be to have the ability to navigate to a given tour. So say to tour number 1000, if you wanted to access that. You can't really do that at the moment. You would have to press show previous.
It's a lot of clicks.
It's a lot of clicks, yeah. And if you toggle this here, it kind of stays fixed to the latest tour, so it shows you the latest as it's finding them.
Awesome.
And you can resume and pause, which is quite nice as well. But
I just had another final question on this. So with the initial location of where the knight is, does that then also change over time for your algorithm?
Yes, so the code is made in such a way that I think ultimately it would change the starting square from A1 to, say, A2, and then to A3 and A4 and so on. But I've never actually found all of the tours that start at A1. So even if we take the subset of the, if we think of the 18 million billion ones, the subset that start at A1 is still a huge number that I haven't actually managed to exhaust. So I think the code at the moment is hard-coded to start simply just at A1. And when it would exhaust all those, it would stop. But it would be a fairly minor change to make it go further than A1 and start at A2, A3, A4, as it's exhausting the previous options. But I haven't run the code enough. I think I might have to run it for a week or a month or so.
That would be an awesome answer to find out how many tours can just A1 produce. Awesome. So shall we dive into the code?
Absolutely. Yep. I'll quit this and go to the code. So it's a relatively simple project, I would say. As you can see, I tried to keep the dependencies clean. I do use OpenG libraries, which I obviously think they are super useful. We have a build spec for exe and installer, and we have a bunch of reusable libraries here. I won't talk about them because even though they're super useful, I'm sure many of us have lots of reusable libraries that we like to use. And the main part of the code is in here. The main GUI, the main VI, is hosted here in this main library. So go ahead and open that. You can see it's the GUI we saw before. And we can go ahead and look at the code. It's a queued message handler. It's basically doing some initialization here. And if everything is good, then there should be no error here on the wire. And if there's no error, then it executes the loops here. Obviously, if there's an error in the initialization, which used to happen when I was developing, then I personally like to have an error case so that I know that the code just goes straight and doesn't really do anything.
Yeah.
So if it's happy with the initialization, it starts the loops. The top loop is an event handling loop, which handles the button presses. For example, the start button that we pressed before is handled here, and enqueues this message to the second loop, which I call the message handling loop. I guess that's the standard name we give to these loops, the EHL and MHL. And then this loop, if we look at start button press, this one, sorry, button press start. If we look here, it's doing a bunch of stuff. I would say I don't think we'll have time to fully explain what it's doing because it's quite an involved application, I guess. But one thing we can see is, for example, it's creating a log file if this Boolean is turned on. So if this Boolean is on, then it's creating a log file, and this is a handler type library which keeps track of its own data. So a reference to that file is stored in a private data memory of this library. And then, very importantly, it sends this command to the third loop here. So it sends the run core command. And if we look down here in the third loop, I call this the core loop. What this loop does, it's quite simple, doesn't do much. Normally, it just sits here in the idle case. But when it receives that run core command, it goes here and executes this VI, which is the crux of the application. It's the core algorithm. As you can see, this algorithm doesn't have error in or out. It just churns out numbers, doesn't do anything else. And it just executes there continuously until it finishes or until you tell it to pause or to stop. So this VI could execute for minutes at a time or hours or however long. And you can see here the starting square is hard-coded, is A1 at the moment, but we could easily change that to another square if we wanted to, and could easily change the code to kind of, as I mentioned before, to move to A2 and A3 if it exhausts the squares. And also what I wanted to do at first was to have a variable size for the chessboard. But I think in the end, if I remember correctly, I haven't looked at this code in about 2 months, so please excuse if I'm not perfectly accurate. But if I remember correctly, I didn't actually implement varying ability for chessboard size. I think that would be a nice feature because with smaller chessboard sizes, you can see more clearly what is happening. As a human, you can kind of keep track of what's happening more easily. For example, with a chessboard size of 5, you could actually, even as a human, you could possibly find very quickly tours as a human. But on an 8x8 chessboard size, which is the standard size used in chess, for a human, it's very hard to find a tour by hand. It's definitely doable, and people have been doing it since, I think, the late 1700s. I think there were some mathematicians and thinkers who studied this problem in the late 1700s, which is quite impressive, obviously long before computers existed. But I did give it a try to kind of solve the problem by hand, and it's very tricky. I think you need kind of pen and paper, or you need to mark the squares you've already been at with maybe some tape or something, because otherwise you kind of get lost and you forget where you've been and where it happened. So,
I think that's quite a handy game to play with kids at some point. Maybe I'll think of that to make it a little game they can.
and see maybe how far you can get until you kind of get trapped, where you kind of reach a dead end.
Yeah, that's it. And then you've got to go backwards again because it's a dead end. Yes. So yeah, awesome.
It's kind of like a virtual maze.
That's it. So we've got another loop at the bottom there, display loop.
Yeah, absolutely. Yeah, we have here a bunch of display loops. I think these are mainly used to draw things on the GUI. I am not necessarily thinking that this is the cleanest implementation. I think could possibly be improved and possibly have a single display loop rather than 2. The reason why I opted to have 2 loops, I believe, is I'm trying to remember now why. I think I had a need to. Yes, I had a need to update different GUI elements at different refresh rates. So the top loop, I think, runs faster than the bottom loop. I think the top loop runs at, if I remember correctly, I think the frequency it runs at is determined by the timeout here in this DQ element. So the timeout is set to 100 milliseconds. And as you can see, if it's a timeout, then it goes to the idle state, which is this one. So this state would execute 10 times a second, thus updating the main GUI elements 10 times a second. For example, this chessboard updates 10 times a second, which I find is quick enough to give the user a sense that something is happening quickly, but not so quick to actually completely make it useless. Because I found if you update, say, 100 times a second, then it's just so fast that it doesn't show you anything really. And the bottom loop, I control the loop rate by this VI here, which simply waits 1 second. Really, so it executes once a second rather than 10 times a second. And this was necessary because I have these indicators, which are the number of moves forward and backward in the last second. So that's why it makes sense to update it only once a second.
Nice. So that was a very good overview of your main VI's architecture there, Petru. I love the simplicity of how it's just a QMH. It passes things down, and you've got a couple of helper loops to update at different rates and things. You know what I'm interested in right now? The main core VI. So I'm more interested right now in how you've gone ahead and yes, it is brute force. We kind of discussed that a little bit. So is it possible to go ahead and navigate around that a little bit?
Sure. So this is the core. This is by far the thing that took me the longest. And I'm sure it's not fully optimized. I'm sure it can be made to run faster. But I did get it to run much faster than my initial implementations. So it's a state machine, essentially. It has these cases here. We start in init, and I guess I won't have time to go into details into everything that's happening, but maybe I can show this VI where it's called perform checks after forward move. Because essentially what the knight is doing, it can be broken down into two simple actions, which are move forward and move backward. And when you move forward, you want to determine which square you want to move to, because often you have more than one option that you can move to. Sometimes you only have one option, so that's simple, but sometimes you have more than one. And when you move backwards, it's a little more simple, because you can only move backwards the way you came. So you only have one option, so you know where to go back. But if we look here, so what this VI does here, it basically kind of assumes that after you've initialized, you can treat the initialization stage, which places you on the square A1, on the initial square that we get from this input. It then says, okay, I'm going to assume that you've just performed the move forward and you've arrived at this square. So then it performs this VI to determine what to do next, whether to keep going forward or to move back. And obviously, because it's the first square, we expect it to move forward to somewhere. So what it does here is, first it checks whether a complete tour has been found. And the way it checks that is simply looks at the total number of squares we have in this array, which I call the tour in progress. And if the number of squares is equal to the total number of squares on the chessboard, which in the case of an 8x8 chessboard is 64. If you've already accumulated 64 squares, then it means you've completed your tour. So therefore, it means you can go to this state, which is the complete tour state. But obviously, this state executes very rarely. Most of the times, you haven't found the complete tour, so you will do something else. It does these checks, and these are actually quite involved checks. I can't really go into too much detail, I don't think, due to time, but basically what speeds up the app massively is to check whether you've already headed down a wrong path, even though you haven't reached a dead end just yet. For example, one example is when you've covered an area of the chessboard in such a way that one of the corners of the chessboard, most often is the corners, that can get missed out by the knight, but all of the chess squares around that corner have been covered, and therefore the corner cannot be accessed anymore. It's an island, as I tend to call them. So it's an island that can't be reached anymore, because you would have to step back on some other squares twice. So therefore, and often you can get that situation even when you've covered, say, only 40 or 50 of the 64 squares. So it's very advantageous to look at the corner squares and determine if they've become islands, and backtrack, realize that you are heading towards a dead end before you've actually reached a dead end. So, and I found that speeds up the app by factors of, say, 100 or 1,000. I don't know. It makes a massive difference. So I think that's pretty much what these checks are trying to do. And if the first check is happy, Actually, I'm just realizing that. So true in this case means we have found one of those islands or one of those unreachable squares.
Sure.
But if we haven't, then you perform the second check on the corners, whether the corner islands are unreachable. And if that is false as well, that's kind of like the happy case where you can still have a chance of going forward. Then it means you can move forward, and we execute this VI to check where to go next. When you have two or more options, we can use this rule, the Warndorf's rule, which is on Wikipedia, and is actually a very useful heuristic to solve this problem. Because initially what I was doing is I was choosing at random where to go next. It wasn't fully at random, so how to say, the knight was having preference for one particular direction in the trigonometric circle of where it can go. Because if you think of the knight as being at the center of a trigonometric circle, then the options it can go to, potentially 8 other squares, can be given a degree on the trigonometric circle. And just for purposes of ensuring my app is deterministic and it does the same thing repeatedly when you run it consecutively, I fixed it to choose the position, the next position that corresponds to the smallest trigonometric angle. So therefore, it was deterministic. It was doing the same thing over and over again, which was really important for debugging. But it was also kind of choosing at random that position, the next position, is not chosen due to any heuristic. It's just kind of stuck in its ways to go one certain direction. And one major improvement was to switch from that to Warnsdorf rule. Sorry about that. Which says to prefer going into potentially dead ends, possibly. So to prefer going into squares that have least potential next forward squares after that. So it's kind of like try to go into a dead end early so that you can back away early and get to a solution more early. It's something I wouldn't have thought of by myself, so I was very happy when I saw it on Wikipedia. And I believe this person, Warnsdorf, was a mathematician, possibly working in it says here in 1823, so obviously long ago, long before computers. So it's quite impressive that some people spent massive amounts of time, I guess, on this problem before computers existed.
Yeah, I can't imagine how they would try and solve it back then as well. So one thing I just wanted to say while you were going through that just then was, something that I talk about at work fairly often is fail often and fail early. And that's kind of what I heard you say just then, is you want to find your islands sooner so that you don't end up going further into the abyss, if you like. Yeah, I like that.
Absolutely. It's nice how it mimics that.
So far, this is still on the first, it's step by step, isn't it? So you've not gone far into your movements. It's every step you're checking, is that going to create a dead end?
Absolutely.
So does the prediction then happen from that step? How many available steps does it have? That's what you've got.
Yes.
Now, you say it takes the one with the lowest angle?
It used to do that, but now it...
Oh, it used to, okay.
Yes, that, yeah.
Yeah, I'm sorry, I misheard that one. Cool, awesome.
And then when it decides here, this next action is usually to move forward because we've just started. So it goes here to move forward, and it executes a series of actions that are actually very similar to what we've just seen. Actually, that VI is the same VI as this one. I know this VI seemed quite involved, but I guess the good news is it is being reused.
Nice.
And this VI again decides what to do next. So whether to move forward again or to move backwards. And it basically selects the next enum value in the state machine transition. So it could possibly go forward again, but also could possibly go backwards. And in the backwards step, we have a very similar layout of the VIs. We actually move backward, which involves changing the data in the memory to kind of make the program think that the knight has moved forward or backward, which involves setting some booleans in a 2D array. Actually, yeah, determining that data structure took me quite a while, and optimizing that data structure. And then it performs some checks after the backwards move, again, to determine whether it's time to move forward again, but on a different path, or to move backwards even more. And when it completes and it has 64 squares in its data structure, then it can go to complete tour, and we can see here it executes here some VI to kind of create that report that we saw earlier, that tells us how long it took to find a tour and other information that eventually makes its way into the text report. You see, we get the time here and other stuff like that. That data is being sent back to the main via a queue. And when we find a tour, we always go back. There's no need to perform a check, because we know, obviously, that we want to move back and possibly find another tour from then on. So yeah, it's really a series of simple steps. As you can see, really, these are the 4 steps. The other 2, exit and be idle, are not doing much. So yeah, these sequence of very simple 4 steps are actually very powerful. Yeah, and can
so if I was to
problem.
Sure. So if you show me the drop-down menu one more time. So I'll try and see if I've understood this correctly then. So in it, you do a initialization to say, check if the current position is valid, which in most cases it is. Yes. Then it says you have to go forward. That's the only option that you currently have. Yes. On move forward, it checks if it's got any potential islands that it's going to face. If it does, then it tells it to go backwards. Otherwise, it tells it to go forward again. Exactly. So if we were to follow a scenario starting from A1, the next location that it is likely to go is C2. That's correct. And that's kind of what your algorithm does, is it always goes to that location, and it kind of almost finishes all of those combinations in those order before it sort of randomizes where to go next, sort of thing. So there's no random nature of that. That's correct. There's no random nature to it. Nice. Sorry, go on. Sorry. No, sorry, please go on. No, I was just going to ask. So with the tour, I know we saw loads and loads of tours being found earlier. So I was wondering if we could follow through finding one tour. So let's say starting at A1, it would find it. It would go to move forward. It would find C2. Yes. Then it would carry on going forward. So each one of those steps where it has multiple locations it could go to, that is the clever part there, isn't it? It's defining and finding where the way you're heading to is a dead end or not. Absolutely. That is the clever part. I think possibly the best way to show that would be to run the program, and we have this option here to pause after every move, which nice. Yeah, I wanted to have that to kind of sanity check my program as I was developing it. So if we go ahead and run this, so if that's debugging through the UI, that's awesome. Yes. So we see that it started at A1, it then moved to C2, and then... Sorry, just to stop you there again. So this is the display loop running at its own update rate. The data from the display loop, from the core loop is going into the display loop through what mechanism? Through a global variable. Nice. Okay. So it doesn't really matter at this point because you're just updating a current value table, so to speak. So there's a all intents and purposes, it's a worm, isn't it? You write in one place, you read in one place.
Yes.
Okay.
Yes.
So if you then, resume.
So when we press resume, it's going to find another point. So it went to A3, and that's as a result of applying Warndorf's rule, which says to move to a square that has least number of possible next squares moving forward. So that's why it prefers going to the edges, mostly to the edges and corners, because those are the squares that have least number of possible next squares, if that makes sense. Whereas if you move to the center, then you move to a place where you have loads of possibilities. So if we press resume again, you see it goes to B1, again on the edge. Then it goes to D2, F1, H2, and so on. So you see it kind of sticks to the edges where the squares with least number of future squares are, which is in accordance with Warndorf's rule. And it kind of leaves the more difficult, if you want, more difficult squares that are in the middle, because there are more options there. It leaves them to the end. Yeah. So
every time it's going forward, if there is a location where there is an island created, then it goes backwards, is what you said?
That is correct, yes. So when it will detect that it doesn't make sense to move forward anymore, then it will move backwards. Yes. But so far, it hasn't detected that condition, so it's still happy to move forward.
Sure. Awesome.
If we keep pressing resume, it will get to a point where we see it moving backwards. So say, I think at around move 50 or 55 or something like that, it might do it. Let's see if I remember correctly. Or I think it actually will find the whole tour. I think, applying Warndorf's rule means you find a whole tour from the first time you try. So the first 64 moves are all forward, which is quite nice. So I think it will find the tour. You can see it's went there, and now it's going to find the last one, and that's the tour completed. And now it's going to go backwards the way it came, and it goes backwards enough to find a different route to complete the tour, which it did.
I see. So you're not re-initializing at all. You're just going backwards until you have a different variation available.
That's correct. Yes.
Nice.
Yes. That obviously saves massive amounts of time. Yeah. So it kind of
I love it. That's yes. Great.
Yeah, you can play by pressing these buttons for minutes or hours. So you can see, I think it would be useful if the GUI showed which square the knight is currently on by having, say, a knight icon on that particular square. I think that would be a very good improvement. At the moment, the only way to know where the knight is to look at this square here. So right now it's on F4, which is here, but obviously that's not very easy to follow. So yeah, that would be potential improvement.
I suppose you're the one writing the requirements for your application, buddy. So yeah, you go ahead and add that on.
Yeah, absolutely. The reason I didn't do it is because obviously I'm using Boolean. It's basically just a 2D array of Booleans here. And I guess displaying custom images on Booleans or using some other controls would have been a bit more tricky. That's why I didn't do it.
Yeah, a picture control might be quite nice. Picture ring, sorry, so that you can have different things on there. Yeah, that's awesome. So can we let it carry on and see how far it gets while we chat away?
Absolutely, absolutely. I'll toggle this off and get it going. It's back up to speed now. And you can kind of see that the CPU is working quite hard, so 23%. Sorry.
That I was going to say that's ignoring the fact that you've got a super beast of a computer as well.
Yeah, the computer is not too bad, but yeah, it's
obscene number of cores, right?
Yeah, I think it's got like 12 cores or something. But yeah, the fans kick in as soon as you start the app. So yeah, you know it's working. One other potential improvement I would like to do one day would be to make this CPU usage even higher. So I don't know, apply some parallelization techniques in LabVIEW, which I haven't really done much before, to try to get that utilization to say 60-70%. I think that would be nice.
So you're effectively, I'm going to call it a tree. I don't know if you have a word for this, for the different tools that you go backwards to. So with the tree structure, you're stepping back up, going backwards to find the next possible diversion, if you like. So with that, how are you? Is that you're just using an array, a 2D array of sorts? What are you using for logging? Yeah, sorry, go on.
Yes, I am using a 2D array of a custom type def cluster, which took a few iterations to get right and get to the kind of smallest amount of data that was necessary. And exactly like you said, Kabul, it's a tree or a graph. It can be modeled from a software engineering point of view. It can be modeled as a graph. And in particular, the algorithm is essentially a depth-first search, or DFS, graph traversing algorithm, which, of course, has been known for decades in computer science. It's a fairly basic algorithm, but still, it's quite fascinating to me. Yeah, so it turns out this problem is simply just a graph problem, really.
So, Petru, what if I wanted to see what you've got, and try and navigate around a little bit, and maybe make my own changes or anything? Have you got this code on a Git repository somewhere available, or?
Unfortunately not. I shared it with some colleagues at Renishaw in some of the sessions we're having, where we kind of share what we're working in the spare time, just for fun. But I haven't really shared it with anyone in the larger community. So yeah, maybe that's something I will look to doing at some point. It's not because I want to keep it secret or anything. I don't know, didn't make that a priority, I guess. So yeah, I might do that in the future.
Of course, if you do, yeah, it would be great to see if any of the viewers right now, if they wanted to, have a look into further upgrading the algorithm, if that is possible. I know you've worked on it, so maybe it's not possible.
I'm sure the community would find dozens of things to improve.
Yeah, and I'm trying to find every reason for us all to, whatever code that we work on, available for the community, so that we can, either use, scrutinize, or modify or upgrade. So yeah, I'll just leave it at that for now. But yeah, it would be great if I could personally just get the code and see how your lower level logic works. If there are ways to speed it up at all, or there are ways that learning-wise we can take that and apply it to another way, another problem, another solution somewhere else. Yeah, it's great.
I will definitely let you know when I upload it.
So total number of moves forward there and total number of moves backwards, they obviously follow each other quite closely, because that's kind of how the algorithm works.
Exactly. Yes.
So with the total number of moves, obviously it's just got up to 20 million. So in 20 million moves on a 64 position chessboard, we're finding 170 odd thousand tours.
That's correct. Yes.
So the numbers just baffle me how many variations we get.
Absolutely. It's baffling. Yes. And as the tours get more difficult to be solved, like we mentioned earlier, the total number of moves to find a new tour increases. So it sometimes, and I also noticed that sometimes it kind of gets to a small, I would say to a small obstacle where it takes more moves than usual to find a new tour, and then it starts rattling through again. So it's kind of like some tours are more difficult than others to be found. Yeah, so in some cases, it might take, I don't know, maybe more than 1,000 moves backwards and forwards to find one tour.
How long have you left this running before?
I think 3 hours.
3 hours. Okay. We're not going to let it run for that long and watch it right now. Awesome. Well, thanks very much for showing us around, Petru. That was great. It was great to look at some of the code that you've got as well, how you've thought through, what the interactions with the UI need to be, what a simple architecture you've got. That's great to see. I love to have a look at your core VI, where the logic you've kind of identified is the same kind of logic where you use sub VIs to use in multiple states as well. That's perfect. Yeah, kudos. Thanks very much for sharing with us today. So I had another question for you while we were talking about thanking and everything else. So obviously you did this in your own time, and you enjoy the algorithmic side of things. So did it cross your mind at all to try and learn another language, maybe Python or something like that, to try and solve problems in that? Because if you look at the community overall in software programming, we've got a huge drive for that. So yeah, my question is, why LabVIEW?
Yes, I did. I am tempted to learn more about other programming languages. I fully agree that as software engineers, we often need to know and work with different programming languages, and there's different strengths with different programming languages. And obviously Python has a massive community, massive user base, and same with, say, C# and .NET programming, and even C, C++, Java, JavaScript. They all have massive communities, so obviously they do have their strong points. I think LabVIEW for me is, because it's what I do in my job, basically, I think is the language I'm most proficient in. And I do think LabVIEW is a general purpose, very powerful language. It's very mature. You can implement any sort of algorithm in it. It's Turing complete. If there's a problem that you can solve in C++ or in Python, then you can solve it in LabVIEW. So yeah, I do think LabVIEW is a very powerful language, and obviously it allows you to build GUIs quickly. And the multi-target support to real-time FPGA is very handy as well, because you can have a complete test system with, say, one Windows computer and multiple real-time targets running one single development environment. So I think that's very powerful.
Yeah, I think one of the things that you showed us today at the very beginning, in fact, when you were opening up your project, was the fact that with the community edition, you can just build an executable, you can build an installer, and you can share your application quite readily as well. Now, when you combine that with the features like Links Toolkit, for example, where you can talk to Raspberry Pis and a whole bunch of other hardware devices like you would with a real-time device, yeah, it's amazing what just as hobbyists we can do with LabVIEW these days. So yeah.
Absolutely. It seems like if you've got LabVIEW Community Edition and an Arduino or a Raspberry Pi and some initiative and some free time, then yeah, you can go a long way.
Hey, listen, again, I want to thank you again for volunteering. I don't know if you've been victimized to come with us today, but thanks for volunteering.
Absolutely. Thank you very much for having me on. It was a pleasure.